The paper we are summarizing today on our YouTube series AI Paper Podcasts is The Information Geometry of Softmax, Probing and Steering.
Authored by Kehoe Park, Todd Neef, Yojun Cho, and Victor Veitch from the University of Chicago and INSEAD.
Exactly. So here's the executive summary for the short form edit. The core problem identified in this work is that most current AI steering techniques,
Like adding a politeness vector to a model.
right, they operate under the assumption that the model's representation space is Euclidean or flat.
Which is completely wrong.
Yeah, the authors argue that models using Softmax, which is almost all LLMs and CLIK models, actually exist in a Bregman geometry. They are dually flat, not Euclidean.
And the consequence of that mismatch is what they call leakage.
Because when you try to steer a specific concept using standard vector addition, you accidentally mess up unrelated concepts. You're essentially taking a shortcut through the wrong geometric structure.
So the solution they propose is dual steering.
Right. Instead of performing vector addition in the primal space, they do it in the dual space, specifically modifying the gradients of the log normalizer.
The result is a method that optimally changes the target concept while mathematically minimizing changes to off-target distributions.
Proven on Gemma-3, 4b, and MetaClip-2. Okay, that is the high-level view.
Yeah.
But we need to switch gears and really get into the weeds here.
We do.
Because this paper is essentially telling us that the mental model we use for thinking inside a neural network is, geometrically flawed. So let's start with that mental model. The linear representation hypothesis.
It has been the dominant mental model for the last decade of mechanistic interpretability.
Right. It is the bread and butter of how we think about features in AI.
The idea is that concepts, things like gender, sentiment, truthfulness, even complex ideas like the Eiffel Tower, they are encoded as directions in a high-dimensional vector space.
And crucially, we treat that space like a physical room. It has height, width, and depth.
It's flat.
Yeah, and we see this everywhere. You have a representation vector, you add a vector to it, and the model behaves differently. It is the classic king minus man plus woman equals queen logic.
We assume you can just slide vectors around. If you want to manipulate the model, you just find that direction vector and add it. Simple linear algebra.
But this paper introduces a really sharp critique. They argue that by doing this, we are committing a type error.
A type error, exactly.
Usually in programming, that means you're trying to do math with two things that aren't the same kind of object, like trying to divide a string of text by an integer.
That is a perfect analogy. Here the error is conflating two different geometric spaces. You have the representation vector, which the paper calls lambda.
And that lives in what is called the primal space.
Right. Then we have the probe vector, let's call it beta, which represents the concept we want to steer. The paper argues that beta is actually a linear operator.
So it lives in the dual space.
Yes. So by adding them together directly,
You are adding a vector from one space to a vector from a completely different space.
it is like trying to add a distance in miles to a temperature in Celsius. In a flat Euclidean world, these spaces coincide so you can get away with it.
It is an approximation that works okay locally.
But because these models use softmax, which involves exponentials and normalization, the geometry is not flat. It is curved. It is an information geometry.
And when you ignore that curvature, your straight line isn't straight anymore. You think you're walking a straight path, but on the curved surface of the probability distribution, you're actually spiraling.
Precisely. And this isn't just a philosophical point about math. It has real consequences for how the model behaves.
I want to ground this for you. The paper uses a really specific example to show why this flat assumption fails, involving interpolating between two images. Can you walk us through the dog experiment?
This is figure 2 in the paper, and it is the absolute best way to visualize why geometry matters. They take an embedding for a black dog.
We will call that X0.
Right, and an embedding for a white dog, X1. Then they just ask what lies exactly in the middle of these 2 points.
In a flat space, the middle is just the average. You take the numbers and average them.
Exactly. If you assume the space is flat and do a primal interpolation, which is what we usually do, the model behaves like an A and D operator. It looks for the intersection.
So at the midpoint, the model predicts a black and white dog.
Yes, it specifically looks for a dog that satisfies both conditions simultaneously. It suppresses features that are unique to just one side.
It is saying what feature is common to both black dogs and white dogs and forces them together, which sounds intuitive until you compare it to the dual interpolation.
Right. If you interpolate in the dual space, the mengeodesic, it behaves like an OR operator. It creates a linear mixture.
It preserves the semantics of both contexts simultaneously.
So instead of trying to find a dog that is logically both black and white, it distributes probability mass over the union of the two concepts.
That is a massive difference in behavior. One acts like an intersection filter, the other acts like a mixture. And the key takeaway here is that if the space were truly flat, these two paths would be identical.
Precisely. The fact that they result in totally different images or tokens proves that the non-Euclidean structure is real and it is governing how the model thinks.
If you ignore it, you are navigating the space with a distorted map.
And that distorted map leads you astray.
So let's talk about where it leads us astray. We mentioned leakage in the intro. If you are trying to steer a model, say you want to turn a description of a dog into a cat, what actually goes wrong when you use the standard Euclidean method? Why is spiraling bad?
This is where we get into off-target effects. The paper uses a text example that I love because it is so clean. Imagine you have a context predicting family members.
Okay.
You want to steer the concept male to female, so father should become mother, uncle should become aunt.
Makes total sense. That is the target. We want to flip the gender bit.
But there are other words in the distribution like friend.
And friend is neutral.
Exactly. It doesn't have a gender component in this context. Ideally, if you steer male to female, the probability of friend should stay exactly the same. It is orthogonal to the change.
But with Euclidean steering,
It doesn't. Standard steering doesn't just shift the target, it distorts the neutral words too.
because you are cutting a straight line through a curved geometry.
Right. You unintentionally boost or suppress unrelated probabilities. They call this a failure of semantic invariance.
They show this visually with CLIP too, right? The cat plus basical image.
Yes, figure 1. This is striking. They have an image that CLIP understands as cat plus bicycle. They try to steer cat to dog.
So you obviously want dog plus bicycle.
Correct. But with Euclidean steering, look at what happens in the middle of the transition. The model gets confused.
It starts predicting a hybrid cat-dog concept.
And crucially, it messes up the bicycle part. It leaks probability mass into totally random off-target concepts before it finally arrives at dog.
So it takes a detour through nonsense land because it's taking a shortcut through the wrong geometry.
Exactly. It creates these transient, high-probability states that shouldn't exist. It assumes the path from cat to dog is a straight line, but in the probability simplex, that straight line cuts through regions that distort the bicycle feature.
Okay, so the diagnosis is crystal clear. We are treating a curved space like it is flat, and that is causing side effects.
Yeah.
Let's talk about the cure. Dual steering. How does it work mathematically?
The equation is simple to state but deep implication. Instead of modifying lambda, the representation vector, we modify phi.
The dual coordinate.
The equation is phi of lambda t equals phi of lambda 0 plus t times beta w.
And what is phi exactly?
Phi is the gradient of the log normalizer, which for Softmax turns out to be the expectation of the unembedding vectors.
Okay.
But geometrically, think of it this way. The dual space is where the linear probes naturally live. When you add the vector here, you are respecting the natural coordinate system of the probability distribution.
Why does this fix the friend problem? Why does this stop the leakage?
This brings us to Theorem 3 in the paper. This is the core theoretical contribution. They prove that dual steering effectively solves a constrained optimization problem,
So it modifies the target concept moving father to mother.
while mathematically minimizing the KL divergence of the off-target distribution.
Can we visualize that? KL divergence is basically a measure of surprise or difference between probability distributions.
Imagine the probability distribution as a set of blocks. You have a family block and a friend block.
Got it.
Inside the family block, you have a split between male and female. Dual steering shifts the divider within the family block, moving mass from male to female, but it keeps the total height of the friend block strictly constant.
Whereas Euclidean steering would squish or stretch the friend block while trying to move the divider.
Exactly. Euclidean steering changes the total probability mass of the concept pairs, which inevitably sucks probability away from friend or pushes it onto friend.
Dual steering enforces that semantic invariance. It says you can change the gender, but you are not allowed to touch the total probability of non-gendered words.
Right.
This sounds perfect theoretically, but the paper mentions a catch in implementation. The dual space isn't infinite, right? It has boundaries.
It does. This is the feasibility constraint. The dual space is the interior of the convex hull of the token embeddings.
In plain English, you can't have a probability distribution that isn't a mix of the things the model knows about.
You can hit a wall where no valid probability distribution exists for the coordinate you are trying to reach.
And when you hit that wall, the math breaks.
Specifically, the Hessian, the matrix that tells us about the curvature, becomes rank deficient. It becomes singular.
This happens because the distribution is often sparse. The model is 99% sure the next word is father or mother, so it essentially ignores the thousands of other dimensions.
The geometry flattens out in those ignored directions, and you get stuck.
So how do they get around the wall?
They use a regularized Newton method, detailed in Algorithm 1. They add a regularization term, alpha I, to the covariance matrix.
Which does what, intuitively?
If the steering hits the boundary, the wall, this regularization term effectively nudges the distribution toward higher entropy.
It makes the model slightly less confident.
By adding a little bit of uncertainty, it pulls the point off the wall back into the interior of the space where the math works, allowing the steering to continue finding a valid path.
That is a clever hack. It is like, I can't move forward because I'm too focused on this one thing, so the algorithm says relax a little, look around, and suddenly the path opens up.
It is a standard trick in optimization, but here it has this specific geometric interpretation of increasing local variance to navigate the convex hull.
Let's look at the scoreboard. They tested this on Gemma-3, 4B and MetaClip-2. What did the results look like?
They looked at two main domains, text and vision. For the LLM, they did tasks like steering English to French or steering a verb to the third-person form.
The metric that really matters here is the KL divergence of the off-target distribution.
Basically, how much did we mess up the context?
Right, and the graphs are stark.
As you push the target probability toward 100%, so you are forcing the model to speak French Euclidean steering, causes the off-target KL divergence to spike.
It destroys the context.
The sentence structure falls apart because it's distorting the grammar words that shouldn't change. Dual steering keeps that divergence low and stable almost all the way to saturation.
And for the vision models, the MetaClip-2 results.
They looked at changing yellow to green or cat to dog. They focused on something called counterfactual sums.
Figure 4 shows this clearly. It measures the total probability mass assigned to the relevant concepts versus the rest of the universe.
With Euclidean steering, as you steer from cat to dog, the total probability of any animal drops in the middle. It suppresses the objects entirely before bringing them back.
Is like the object momentarily disappears. That's the detour we talked about.
Exactly. Dual steering maintains that total mass. It effectively slides the probability from cat to dog without leaking it into random images of fire hydrants or trees. It creates a smooth semantic transition.
There was also an analysis of cosine similarity, specifically in the dual space.
Yes, figure 5. This validates the theory. When you perform dual steering, the change in the model's state actually aligns with the concept direction in the dual space.
That sounds tautological, but it isn't.
When you do Euclidean steering, the path gets warped. It does not align with the concept direction in the dual space because the Hessian, the curvature, twists it. Dual steering cuts straight through the information geometry.
So zooming out, we have a paper that says our fundamental intuition about vector arithmetic and AI is, strictly speaking, wrong, or at least an approximation that breaks down when we push it.
That is the big picture. This isn't just a new steering method. It is a critique of the flat space assumption.
We spend so much time looking at PCA plots and vector additions, assuming these are arrows in a flat room.
They aren't. They are arrows on a twisted, curved surface.
And if we want reliable control, if we want to make sure that making a model helpful doesn't accidentally make it gullible via leakage, we need to respect that curvature.
Exactly. We have to respect the intrinsic geometry of how the model actually computes probabilities, not just the vector space we imagine it lives in. But I will add a caveat, which the authors mention.
What is that?
This strictly applies to softmax layers right now. That is where the exponential family geometry comes from. But LLMs are deep. They have attention layers, MLPs, layer norms.
How does this Bregman geometry propagate backwards through the network?
That is the billion-dollar question. Does the attention mechanism create its own geometry? If we steer an intermediate layer using Euclidean addition, does it wash out by the time it hits the softmax?
This paper solves the geometry at the output, but the internal geometry of the thinking process is still an open frontier.
It is.
Well, for anyone listening who wants to crack that frontier or just wants to play with dual steering, the authors have released their code. You can find it at github.com/keopark/dual steering.
And of course, read the full paper for the proofs on Bregman duality. It is heavy math, but beautiful if you are into that.
Now, I'll leave you with a final thought to mull over. If the output space of these models is this profoundly curved, what does that imply about the geometry of human language and the concepts we feed into the model in the first place? Maybe our own cognitive space isn't as flat as we like to think either.
That is a fascinating angle.
See you in the next deep dive on AI Paper Podcasts.